Just as a quick review before we start talking about Raman spectroscopy, what we had talked about previously was UV and vis spectroscopy, where you're talking about the possibilities for the absorption of a resonant photon, one that matched the exact delta E of the quantum difference between the two electronic states. Absorption was when we would absorb and go from a lower electronic state, and we would absorb the energy of the photon to promote us into an excited state. We also talked about emission, in which the photon would be emitted when the energy of the bond went from a higher excited state to a lower excited state. We could use both of these in quantitative analysis for quantitation using Beer's law. The difference is absorbance, because of the geometry of the instrumentation, would permit us really broad applicability. Everything absorbs in the UV and vis. Some things are accessible, some things aren't, but it's very broadly applicable. Emission, or fluorescence, is not as broadly applicable. Not everything will fluoresce, but because of the geometry of the instrumentation, this gives us very high sensitivity. When we talk about IR, what we're talking about so far has been the absorbance between vibrational states within a single bond. We don't change the bond we're looking at. We're just looking at the delta E between that. And that's a much smaller delta E. We said on the order of about 1/10 of as much energy or so. That delta E can be described in joules, or in the case of IR spectroscopy, sometimes we use another unit, which is reciprocal centimeters. A carbonyl, for example, a C double bond O, has an energy difference which is equivalent to about 1700 reciprocal centimeters. That is the delta E. Generally speaking, we do not use IR spectroscopy as a method of quantitative analysis because its power for structural analysis is so great, and the instrumentation used for it fairly limits our ability to do things like aqueous solutions. But we can start discussing what about the equivalent of a fluorescence technique, which is based on vibrational quanta. And this is the basis of Raman spectroscopy for quantitative analysis, is looking at using the fluorescence technique, which has the specificity of IR vibrational modes. The concept of Raman spectroscopy comes about from an observation of what happens if you put a photon in that is not resonant with the energy difference between the two electronic states. If I put this photon in, it is actually resonant with that delta E and can be absorbed. But what happens if I put a photon in which does not have enough energy? Well, we've already talked about the fact that non-resonant photons will interact with the molecule, but there will be no net absorption over time, so the photon is not absorbed. That energy is not absorbed by the molecule, so it appears to just keep going straight on through. But just because it didn't get absorbed by the molecule doesn't mean it didn't interact with the molecule. And some molecules, specifically those that have changes in polarizability as the bond stretches, have been observed to redirect those photons. So the photon, the non-resonant photon, goes in, but it gets redirected in opposite directions. This is called Rayleigh scattering. As if the photon got scattered by the molecule. No energy change. It has the exact same energy as when it went in, so it just looks like it got redirected. But in a sense, that Rayleigh scattering almost looks like the photon was absorbed and went up to some higher energy and then was fluoresced in any direction. Of course, it's not going to any real state. It only goes up to the energy that the photon gave it and then simply falls back down. But if it goes up and then falls back down, it's almost as though it was absorbed into a virtual state when we're just hung out for a femtosecond or so and then was re-released back to the ground state. This virtual state is the basis of Raman spectroscopy. If it goes up and comes down, then we can actually start observing the possibility that when it is re-released, it may actually only be re-released back down to a higher vibrational state. Again, note that it did not change electronic state, but the energy of the re-released photon would be different than that of the incoming photon. It would be less by some delta E, specifically the delta E of the vibrational state. So if we had a non-resonant photon go in, and when it was re-released, it fell down to a higher lying vibrational state, the photon that would be released would be redshifted towards longer wavelengths, and that would be called Stokes emission, where the energy of the Stokes emission would be equal to the energy in minus the energy of the IR. It's also possible that if the molecule started out in a higher vibrational state, that when it fell down from the virtual state, it could actually fall to a lower lying vibrational state, emitting a photon which is actually higher energy than the incoming photon. That energy is called anti-Stokes. And anti-Stokes emission, we'll call it E out, would be equal to the energy of the input photon plus that delta E of the IR. The Rayleigh would be the same as the energy coming in. The Stokes energy would be decreased because it fell to a higher lying vibrational state, and so therefore is redshifted by the IR photon. The anti-Stokes the energy would be increased, and therefore the emission would be blue shifted. The amount of shift in the visible spectrum is therefore due to the energy of the vibrational mode. That means that the shift is highly structurally specific, and that structural specificity in the amount of the red shift and the blue shift of a fluorescent photon can be used to both quantify and specify the molecule of study. Let's look at a specific. We have a ground vibration, ground state, and we put in a photon of 632 nanometers. Let's say that photon of 632 nanometers is not enough to reach the next electronic state. It will only bring the molecule up to a virtual state. If it is re-released in a Stokes emission, then the energy released will be different by the delta E of the IR. In a specific case, we can talk about a carbonyl. We already know something about the carbonyl. It has a vibrational frequency or an energy term which is equal to 1700 reciprocal centimeters. That's 1700 reciprocal centimeters is equivalent to the energy of that IR difference. If we put in 632 nanometers, we know we can convert that into energy using C equals lambda nu and E equals H nu, but we can also just convert it into that same energy unit. Remember, reciprocal centimeters is an energy-related unit. So, all we have to do to convert it into that unit is take 1 over 632, that would get us to reciprocal nanometers, and then if we convert it to centimeters, where there's 10 to the 7th nanometers per centimeter, 632 nanometers is equivalent to 15,823 reciprocal centimeters. So this difference, this energy of this photon, is about 15,823 reciprocal centimeters in energy. If we're talking about the Stokes emission, the energy out is going to be equal to the energy in minus the energy of the IR. This becomes very simple then. 15,823 reciprocal centimeters minus the energy of the IR, which is 1,700 reciprocal centimeters. That means the energy of the Stokes emission is equal to 14,123 reciprocal centimeters. That in and of itself may not seem very interesting, but we can also convert this back to wavelength in nanometers. All we have to do is take the reciprocal of 1400, 123 reciprocal centimeters, to get us to a wavelength in nanometers, in centimeters, and then once again, this would give us 708 nanometers. All right, so if we put a photon in, which is 632 nanometers, the Stokes emission would be redshifted towards longer wavelengths and come out at 708 nanometers. This specific shift would be due to this specific energy, which is structurally dependent. Likewise, we can also do the anti-Stokes emission. Where the E out is going to be blue shifted by the amount of the IR. So in anti-Stokes, we're going to start with the 15,823 reciprocal centimeter photon going in, or 632 nanometers, and it's going to be blue shifted because the output is going to be slightly longer. That means that E out would be 15,823 plus 1,700 gives me 17,523 as the energy of the anti-Stokes emission. And then if I convert that I get to a wavelength of 571 nanometers. So, if we put the Rayleigh scattering in, and some of it comes straight back at the exact same wavelength, some of it is going to be redshifted by the carbonyl energy to 708, and some of it will be blue shifted towards shorter wavelength to 571 nanometers.